So moving on. So this is kind of a summary of everything that I've said. So when we do delta, so this is the Greek letter delta, and that means change. We use the Greek letter delta to indicate a change. And specifically, it's always final minus initial, always. So I could have some other type of state function that I haven't defined yet, maybe capital X, right? Because capital letter tells me it's a state function. Whatever X is, pressure, volume, whatever, right? Temperature. It's always going to be final. So I'll say X final minus X initial, okay? So now, here we have the system inside this little box, okay? And then outside of the system is the surroundings. And outside the surroundings is everything else, the entire freaking universe, okay? It's a very boring world in this thermodynamics world here, okay? All the same, the universe is in contact with the surroundings, and the surroundings are in contact with the system. And in the case of this being an either open or closed system, right, because those can exchange energy, when energy goes from the surroundings to the system, as viewed by the system, the delta E of the system will increase. So in other words, the final state is now greater than the initial state. That gives us a positive quantity. We call this endothermic, meaning heat is moving into the system, okay? But as is the case, as is the opposite case, okay, when energy leaves the system and goes to the surroundings, then the final state of the system will be less than the initial state, and that will be negative. So heat is leaving the system and going out to the surroundings, which is why we call it exothermic. And so I already gave you one example of an exothermic reaction, combustion. All combustion reactions are exothermic, right? You light something on fire and it releases heat back out to the surroundings. So the fuel, the molecules that are burning themselves, those are the system. Everything else is the surroundings, okay? And so this gets us to now, I was just one slide ahead of myself. So just a little bit more on system surroundings and energy transfer with respect to phase transitions. As we might imagine, there are exothermic or endothermic phase transitions. You're already familiar with several endothermic phase transitions. So for example, how do you boil water? You put heat in, right? A pot of water will not spontaneously start boiling, okay? So that's this diagram right here, going from liquid to gas, vaporization, right? Which, we could also call boiling. So heat has got to go in to boil that water, okay? Well, what about melting some ice? Yeah, you guessed it, right? An ice cube at 0 degrees Celsius will not spontaneously melt on its own unless you put heat into it. And that can actually be achieved by taking that ice cube right out of your freezer and setting it on a warm bench or countertop, okay? That ice cube, because it is colder than the countertop, right, back to that very first slide I showed you, right? If the countertop is 25 degrees Celsius and the ice cube is 0 degrees Celsius, okay, heat will flow from the hot object to the cold object, so it will melt the ice cube. Heat will go in to melt the ice cube. Similarly for sublimation, when you go directly from a solid to a gas, that requires heat to go in. But now if you think about all the opposite of these, I think these are all less intuitive, okay? So back to that freezing example now. If we want to freeze some water, for example, we have to remove heat from it, right? We cannot cool things down by transferring heat from a cold object to a hot object. It doesn't work like that, okay? The heat has to go from hot too cold. So we have to remove the heat somehow, and that is achieved by the heat leaving the system and entering the surroundings. Okay? Similarly with a gas condensing, okay? So if we know that we have to put heat in to boil something, when steam condenses, like you imagine maybe steam condensing on the windshield of your car, for example, that's going to release heat, which you don't really think about. That's counterintuitive, but it will in fact release heat out to the surroundings. And we'll explore more of why that is in Chem 110. We'll get into those details and a lot more when you take Chem 110.